From the video about compressive and splitting tensile strength tests, you learnt two mechanical methods that measure how strong concrete is. Another way to understand the mechanical property of concrete more closely is to measure the behavior in its elastic state. This means, unlike the compressive and splitting tensile strength tests, we monitor the continuous size changes as a result of force applied on the concrete cylinder. When the concrete cylinder is within its elastic state, we measure the longitudinal stress, longitudinal strain, and transverse strain continuously to calculate the static modulus of elasticity, or the E-value, and Poisson's ratio. Engineers use the E-value and Poisson ratio within the elastic stage to design the sizes of structural concrete members and to design the quantity of reinforcement in the concrete members. There are 3 steps which must be followed strictly to perform the test. The first step is specimen preparation and positioning. The second step is loading and measurement. The last step is calculation. The first step is preparation and positioning. A. Cap the surface of the cylinder to flatten the contact surface. Let the cylinder cool down overnight until the test is carried out the next day. If the surface is not flat, it may result in imbalanced stress concentration. B. Apply epoxy at the middle of the cylinder for fixing of strain gauge in the transverse direction. Let it dry 1 day before the test. C. Use the caliper to take the average of the 3 diameters at the center, upper and bottom parts of the specimen. Rotate the specimen by 90 degrees and repeat the measurement. Use the average value to calculate the cross-sectional area. D. Measure the length of the specimen, including the caps. Rotate the specimen by 90 degrees and repeat the measurement. Use the average value to calculate the length. Note that the length to diameter ratio should be between 2 to 5. E. If you are interested only in the E-value and Poisson's ratio, use 3 companion specimens from the same batch of concrete to determine the average of compressive strength. F. Correct the strength value if you use different shape and size of companion specimen. This step must be done before the test for the E-value. For example, multiply the cube strength value by 0.8 if the size of the cube is 100 mm and the cylinder for E-value test is 200 mm. G. Install the strain gauge in the transverse direction and at the middle of the cylinder. H. Install the frame with linear variable differential transformer (LVDT) in the longitudinal direction. I. Place the specimen on the lower platen of the testing machine. Carefully align the axis of the specimen with the center of thrust over the spherically seated upper platen. J. As the lower platen is brought slowly to bear upon the specimen, rotate the movable portion of the block gently by hand so that uniform seating is obtained. K. Connect the LVDT and the strain gauge to the data logger. The second step is loading and measurement. A. Set the initial compressive machine LVDT and strain gauge reading to 0. B. Apply the basic stress S1 of 0.5 Newton per mm square and record the LVDT and strain gauge readings. C. Continue the load at a constant rate between 0.6 plus or minus 0.4 Newton per mm square per second. D. When the applied load reaches 1/3 of the compressive strength Fc, determined from the companion specimens, stop the loading to maintain the specimen in elastic state. E. Maintain the load S2 for 60 seconds. If the individual longitudinal strains deviate outside a range of plus or minus 10% of their mean value, recenter the test specimen and repeat the test. F. Reduce the load at the same rate as during loading to the level of the basic stress S1. This is the completion of the first pre-loading cycle. G. Carry out 2 pre-loading cycles with the same loading and unloading rate. Maintain both S1 and S2 at constant levels for 60 seconds. And only take readings of stress and strain in the last cycle. H. If you only require the E value and the Posson ratio, beyond the elastic state, continue loading until the stress exceeds the peak and declines. But be cautious that the LVDT may be damaged suddenly when the specimen yields. Also, if the peak of the stress differs from Fc of companion specimen by more than 20%, this fact shall be reported. The last step is calculation. Before we start to do the calculation, the definitions of the following terms should be introduced. Stress is the load level divided by the cross-sectional area mentioned by the diameter of the cylinder. Longitudinal strain is the longitudinal deformation divided by the length of the frame. Longitudinal deformation is measured by the LVDT installed in longitudinal direction. Transverse strain is the transverse deformation divided by the length of the strain gauge. Transverse deformation is measured by the strain gauge. I. Now we go back to calculate the E value. First, we plot the stress longitudinal strain curve. Second, determine stress S2 and strain E2 corresponding to 1/3 of concrete strength of the companion concrete. Third, determine stress S1 which is 0.5 Newton per mm square, corresponding to the longitudinal strain E1. Finally, calculate the E value by this equation, which is the slope of the curve. J. Now we calculate the Posson ratio. First, we plot the transverse strain against the longitudinal strain curve, which is usually linear. Second, corresponding to stress S2, determine the transverse strain ET2 and longitudinal strain E2. Third, determine the transverse strain ET1 and longitudinal strain E1, corresponding to stress S1, which is 0.5 Newton per mm square. Finally, calculate Poisson's ratio by the slope of the curve. Safety should also be taken into account during the experiment. When the equipment is in operation, the personnel must wear a pair of safety shoes, safety goggles, and close the safeguard in front of the compression machine. If you intend to break the concrete beyond elastic state, always wear an earmuff and alert your neighbours to be aware of the sudden bursting noise. There are numerous factors that affect the E value and Poisson's ratio of concrete. These factors are basically the same as those discussed in the video about compressive strength. In general, a higher concrete strength implies a higher E value, which means that the concrete can take a higher stress level for a unit strain. We have introduced the experiment by means of applying load with constant load control. On the other hand, if you are interested in the delicate deformation of your concrete specimens, you can switch the loader mode from constant load control to constant displacement control. Then more detailed measurement can be made. In this case, the stress-strain curve will be different, but same as before, a higher concrete strength implies a higher E value. The descending part is also steeper in concrete with higher strength. This means that higher strength concrete is more brittle. This factor is important in the structural design to resist seismic activity. Now we come back to the E value and Posson ratio. For normal concrete, we can generalize the relationship between strength and E value. The rule of thumb is that the harder and denser the concrete is, the higher is the compressive strength and modulus of the elasticity that the concrete attains. A higher E value also leads to a lower Posson ratio, which means a smaller transverse strain relative to a unit change of longitudinal strain. So far, we have discussed the usefulness and procedures of the E value and Poisson's ratio test, and demonstrated the detailed steps for the test. This test is used extensively all over the world and standardized in the British Standards, ASTM, and Hong Kong Construction Standards, from which you can find the principles and working details of the E value and Poisson's ratio test. By watching this short video, we hope you have been able to understand 3 main points: the 3-step procedures and the underlying principles of the E-value and Poisson's ratio, the reasons for carrying out the E-value and Poisson's ratio test, and the major factors affecting the E-value and Poisson's ratio. That's all for this video. Thanks for watching.